Hi, how we doing, Algebra 2 honors? So just wanted to touch base and put together a video with some of the things that we talked about today in class regarding quadratic functions and transformations. And so, keeping in mind that Algebra 2 is a lot, the first semester anyway, is a lot like Algebra 1 all over again, just faster. Some of these things will sound very familiar to you. So when we think about a quadratic function, I just want to remind you guys again, and if you didn't get a chance to write this down in class, feel free to take some notes during this video. So we've just spent a couple chapters looking at linear functions, and now we're going to move on to a different type of function, a quadratic function. And it's written in this form. F of x equals a times the quantity x minus h, close parentheses, squared, plus k. And a reminder that a cannot be equal to 0. So f of x equals a times the quantity x minus h, quantity squared, plus k. And we remind ourselves also that when we have a quadratic function, that input variable, the x, is always squared. It's one of the ways that we can tell that we're working with a quadratic. So we spent a little bit of time a couple weeks ago thinking about parent functions. Right? The simplest example of a function that has all the characteristics of that function. And we talked a little bit about absolute value. So we reminded ourselves of what absolute value means, and then what the function looks like, a V-shaped thing that opens up or down. And we worked with transforming those functions a little bit. So just again to remind ourselves, the linear function parent is the line y equals x. And it contains points like -2, -2, -1, -1, 0, 0, right? Y equals x, so the x and y are going to be the same, and that results in this line with a slope of 1. Notice that it goes through the origin. Our quadratic parent function is f of x equals x squared, and it's going to be this U-shaped graph that has its vertex at the origin. So if we use -2, -1, 0, 1, and 2 for our inputs, we get -2, 4, because -2 squared is 4. -1 squared is 1, so that's a point that's on the curve. 0, 0, and then 1 squared is 1, 2 squared is 4. So a couple of things about these functions. You may remember back in Algebra 1 when you first started graphing quadratics and understanding that you were going to get this parabola, this U-shaped thing. We started off by plotting 5 points. You took 5 inputs for your x's, substituted those in, simplified, got your y's, plotted your ordered pairs, and then drew in your smooth curve. And you notice that it was a little bit tedious, right? If you chose your 5 points intentionally, working around the axis of symmetry, you only needed to substitute in 3. And if you caught a break, if 0 is one of your inputs, then only 2. But still, it took a little bit of work. And so now we kind of understand with the ability to transform functions that we can get a decent idea of what these functions are going to look like just from their equation. So I'd like to take a look at a couple of translations, horizontal and vertical. So when we've got a function and we add or subtract something from the x value before we square it, so x minus h quantity squared, that has the effect of moving our graph left or right. Okay? If the h value is positive, it moves to the right. If the h value is negative, it moves to the left. And you want to step lightly here. The formula is written x minus h. So if h is positive 3, this is going to read x minus 3. It looks negative to our eye, and our mind reads it as negative, right? But x minus a positive number, right? So we're moving to the right. Sometimes it helps to keep in mind with a horizontal movement, it's like the opposite of what seems intuitive to you. Vertical shift, if I add or subtract a number after I've squared this value, that is the effect of moving the graph up or down. A positive k value moves up, negative k value is going to move down. And so with the h and the k, we get an idea of how this graph is shifting left, right, and up, down. And I'm reminded a little bit of, this goes back probably 10 years and standing in my math class with an overhead projector and actually 2 plastic transparencies, and I put the 2 graphs on top of one another, and I would actually shift them around to show the transformation of the quadratic. And at the time, I was reading a lot of futuristic stuff. And I told my students, hey, I go, this isn't going to happen when you guys are in school, but your kids definitely. I said, instead of taking all this time in class to plot these out by hand and then not really understanding how they're moving, you see how I'm moving these plastic shapes around? So one of these days, like in school, we're just going to have this little handheld computer. You're just going to take your finger and move these around the screen. And they were like, you will not. That will never happen. But they agreed it would be cool. Like I've been waiting for this moment for literally like half of my teaching career, 10 years or so. And we're finally there. And so I want to shift over and remind you guys of a site we've used a handful of times. The Desmos graphing calculator. We obviously use the Desmos activities quite a bit that have the functionality of the calculator built in, but the calculator does stand alone on its own. And so this website, desmos.com, DESMOS, takes you to this page. And if you click that button for graphing calculator, here's what you'll see. So this should look kind of familiar for those of you who've been in class with me. So the right-hand side of the screen, you've got your coordinate plane. And on the left-hand side of the screen, we've got an area where we can enter tables, expressions, text, whatever. So let me go ahead and type in y equals x squared. So here's our parent function for a quadratic. So this red curve, and you could see that it has its vertex at the origin, and it contains points like 1, 1, and 2, 4, which we saw earlier. Let me go ahead and type in another one. Y equals x plus 3 quantity squared plus 1. And so in class, I asked you, how is the blue graph different from the red? And several of you told me, well, it's shifted. And some people said, well, it's moved above. Other people said it's left and up. So we did a really good job of describing the direction of the movement. What we can also do is describe the distance. Okay. And so as I take a look at my vertex of my parent function 0, 0, some of you know that in Desmos, if you hover over a point or you click on a point, it'll display the coordinates. So, and some of those points that are critical points, like for instance, the vertex is the turning point of the parabola. So it's going to jump out at us, -3, 1. If we take a look over here, I see 3 and 1 right in the equation. And wow, that's like a creepy coincidence. I can't believe that. Like, that's so weird that the vertex is at -3, 1, and then 3 and 1 are right in the equation. Like, I wonder if that happens all the time. And obviously, you guys have put up with my smart aleckiness long enough that you know where I'm going with this. Of course it is. And so that type of function that I've typed in the box for you, y equals quantity x plus 3 squared plus 1, is called vertex form of a quadratic. So you've been working with standard form in Algebra 1, and now we'll also be using vertex form, right? Which, just like in slope-intercept form, if you know where to look, you get some important information about the graph. Same thing with vertex form of a parabola. So I want to do one more thing. In this next row, I'm going to type in y equals x squared plus 6x plus 10. And all of a sudden, that graph that was blue, it looks like it turned green. What happened here? Well, I'm going to go ahead and hide the green graph for a minute just so we can verify that, yeah, that's actually the exact same graph. And if we were to expand out x plus 3 squared, you get x squared plus 6x plus 9 plus 1. That's x squared plus 6x plus 10. So these two are different forms of the exact same function. And one of the things that you notice here is in vertex form, wow, this gives us some information that we don't get from this graph, specifically where the vertex is located. So that's some really, really useful information. Here we are in the 21st century, and especially, teaching and learning remotely, it really, really helps to have access to technology like the Desmos graphing calculator to be able to make some sense of some of these things that we're working with, especially transforming functions and seeing what different inputs do to those functions. I want to do one last thing. I'm going to open up one more row, and I'm going to go y equals -1/2, and then parentheses x plus 3 close parentheses squared plus 1. So one of the things that you notice as we take a look at this purple graph, one of the things pretty clearly is it's quote unquote upside down. And it appears to be wider than this graph. So now we see what the value of a in our function does. So negative, the graph is going to be reflected over the x-axis, or open down, as we said in Algebra 1. And the a value itself, in this case, negative 1/2, if the absolute value of a is less than 1, between 0 and 1, that's going to cause the graph to be wider than the parent function. If the absolute value is greater than 1, this graph is going to be more narrow. So a little bit of a look at what we can see. I'm going to jump on over the activity we were doing earlier today, of what we can see from the function rule itself, the actual equation that makes the parabola. Chromebook a little laggy today, unfortunately. So a little bit earlier today, we were working through a Desmos activity, and we were trying to use what we had learned shrink down my inset box, to be able to write equations of parabolas that matched these points. So here's our parent function, y equals x squared. Right? Then we worked on matching these blue points. And one of the things that we pointed out was these blue points seem to be arranged in the same pattern as these red points. And we also noticed that the matching points were exactly 3 units above. 1, 2, 3. 1, 2, 3. They're matching points on the red curve. So it appears that this blue graph has shifted 3 units up. Well, how does that happen? How do we represent that with our equation? So y equals x squared, and then we know that the k value moves this up or down. So we're going to go plus 3. And in this exercise, we could check our work by pressing the blue button. And yeah, we go right through there. Well, how about these green points? If I look at the vertex, 1, 2, 3, 4, it appears that it's moved over 4 units to the right. Well, let's remind ourselves, how do we make that happen? So to get a horizontal shift, we're going to add or subtract from the x before we square that expression. So y equals, and we're going to go x minus 4, right? If we want to move it to the right, it's going to be minus a positive. If we're going to move it left, it's going to be minus a negative, which would create addition inside of those parentheses. So y equals x minus 4 quantity squared. And that hits that green, those 3 green points. One more that I wanted to take a look at. We didn't get a chance to do this in my first period class. Third hour did get a look at this. So here we were given 3 points, and no longer were they in that same kind of familiar pattern. They're offset from each other, so we don't have the symmetry. We are told that this is our vertex. And what we were asked to do is to plot a parabola through these points by writing an equation and then check our work. So what's our process here? So one of the things that we know is we can identify how the vertex moved, okay, and write an equation in vertex form, x minus h quantity squared plus k. So if I look at how my scale is set up, these major grid lines are 4. So each of the minor grid lines are 1. So I can see that my vertex is at 4 on the x-axis and then down 2. So the point is 4, negative 2. Okay, so y equals, let's go x minus 4, quantity squared, and then minus 2, and see where that takes us. So we've definitely hit the vertex. And this is an interesting point because that a value changes a lot of things about the graph. Right? We might hit the vertex but not have the exact same